Hello everybody, my name is Noussaiba Mennai. I am a PhD student at the University of Skikda, Algeria. On behalf of my co-authors, I would like to present our conference paper entitled Intelligent Control for Enhanced Phase-Locked Loop Performance in Grid-Connected Inverters. This is what we are going to cover during this presentation. The amount of power used worldwide is rising quickly, surpassing the capacity that traditional fossil fuels can accommodate. In response to this challenge, modern environmental rules advise widespread use of renewable energy sources in context of distributed generation systems, DGs, or microgrids. The integration of renewable energy sources into the grid is essential. However, it requires careful placement, improved grid-connected inverter control techniques, and the most important is a synchronization process to prevent disruptions and instability in the utility grid. There have been a lot of studies done in the past few years on phase-locked loops, PLLs, which play a critical role in the grid-connected power converters, and it enables also a precise synchronization of this converter with the grid. However, recent PLL studies in grid-connected power converters heavily lean on PLLs equipped with conventional proportional integral or PI controllers, which have some limitations in their transit behavior. Also, they are highly sensitive to varying parameters and sudden fluctuations. For example, in frequency or voltage, especially during, for example, grid faults. On the other hand, studies introducing a fuzzy logic approach to the PLL lack depth in modeling and practical applicability in the real three-phase grid-connected inverters. So the aim and the purpose of this paper is to enhance the performance of the grid-connected inverters synchronization unit. Namely, here we are talking about the synchronous reference frame SRF-PLL, which is the most used one, by placing the traditional PI controller with the fuzzy logic controller. So to do so, both controllers were designed and tuned. Then simulation results were obtained during in a Matlab Simulink environment by integrating these two PLLs into a current controller of a 1 megawatt 3-phase grid connected voltage source inverter. And finally, we are going to finish with comparing the results. Moving on to the second section of this presentation, but first of all, let's take a look at the basic concept of a PLL algorithm. What is a PLL algorithm? As you can see here in the figure, that it is a closed loop algorithm which automatically regulates the phase of an output signal to be equal to that of an input signal. It is composed of three main components here: the phase detector, the loop filter, and the voltage controlled oscillator VCO. Moving on to the SRF-PLL, it is similar to the basic PLL, but here it is we are working in a synchronous reference frame SRF. So to model this SRF-PLL, Clark and Park transformations are used to convert the grid voltages VA, VB, and VC to the stationary reference frame and to get V alpha beta. Then convert them by using Park transformation to the SRF components VD and VQ. The idea of the SRF-PLL, it is by lining up the D-axis voltage VD with that of the first phase VA, base voltage VA, it is possible to determine the phase angle by forcing the VQ to be equal to 0. Here, to force the VQ to be equal to 0, we use the PI controller. Okay, here we add the feed forward frequency omega 0. Then by integrating the output, we get the phase angle. The modulo here, it is used only to wrap the phase angle between 0 and 2 pi. Tuning of the PI controller gain. So since we are talking about PI control, we have to tune and to get the PI controller gain KP and KI. So to do so, we are using here the approximation sign delta theta equal to delta theta if delta theta it is almost equal to 0. So by applying this approximation, we get the approximate values of VD and VQ. that we are going to use them to get a simplified model here of the SRF-PLL. It is a closed loop model, of course. Then by getting the transfer function of this closed loop, by matching the denominator of this transfer function to the standard form of a second order system, we get the K, P, and Ki gains of the PI controller. Moving on to the design of the proposed regulator here, the fuzzy logic-based SRF-PLL. So in this section, the PI controller of the DQ-PLL is substituted by the fuzzy logic controller FLC. Here, as you can see here in the figure number 5, these are the changes that we have implemented to the traditional one. So the first input of this controller, the FLC, is the error, as we can see here. It is representing the difference between the reference value 0 of that we need VQ. We are forcing VQ to be equal to 0, and the measured value of the quadrature component of the voltage. The second input is the change of the error CE, which is the derivative of the error. So to sum up the design steps of this proposed FLC controller, we must follow 3 main stages: the fuzzification, the inference engine and rule base, and finally the defuzzification. The fuzzification in this study, we have used the 5 linguistic variables to define the input and output variables as follow. NB a negative big, NS negative small, Z it is 0, PS positive small, PB positive big. So these are the 3 membership functions of a triangular shape for the error, the change in error, and the output. The inference engine and rule base. The inference of this study is done by using the Mamdani inference engine and the max-min implication technique, where the AND operator is represented by the mean operation, and the OR operator is represented by the max operation. This is the table that which represent the 25 fuzzy rules that determine the FLC's output depending on its 2 inputs, the error and the change in the error. And this is the control surface of the fuzzy rule base. Finally, the defuzzification. In this research, the center of gravity, COG, is used during the defuzzification process to transform the fuzzy output results generated by the Mamdani inference engine in the form of a membership functions into a numerical value. All the previous design steps was implemented by Matlab fuzzy logic toolbox. Simulation results. So to test the designed PLLs, the SRF-based and the FLC-based, both of them were placed in the control block of a predefined model of a 3-phase grid connected 2-level voltage source inverter. Okay. To evaluate the performance of each one, simulation tests were conducted in the Matlab Simulink environment during normal grid conditions to evaluate their transits and steady-state responses. These are the parameters of the previous model. First, let's start with the results that we have get from PI-based SRF-PLL, or the traditional one. So as we can see here in figure number 9, the plots demonstrate that the SRF-PLL successfully detected the grid voltage phase accurately, as we can see here. Also, the PI controller effectively regulated the quadrature voltage component, and it is forced after a half a cycle or 0.01 second with overshoot, as we can see. Then at the steady state we get VQ equal to 0. On the other hand, as the VQ is forced to be equal to 0, the direct component VD becomes constant after a slight drop, as you can see here in the transit state corresponding, and after that it becomes equal to 1 per unit, which corresponds very well to the peak value of the grid voltage VM, and as we have mentioned earlier in the approximation. The results for the FLC-based SRF-PLL, it was similar to the previous one, the traditional one. It was also able to track accurately the phase and to lock into the grid phase, as we can see here in figure 10a. However, as you can see here, notably, there is a marked improvement in the plot of the VQ here, where the VQ was forced to be equal to 0 with no overshoot. As you can see, it was end in less than half a cycle. Additionally, the VD, it remains constant at 1 per unit without any transit disturbance. There is no transit disturbance here in the plot of the direct component of the voltage, indicating that the FLC yields better results than the PI controller at this stage. The frequency for both PLLs was plotted and compared to compare their performance inside this system. As you can see here by the figure 11, the frequency responses and performance characteristics of both PLL, it can be confirmed that the proposed FLC controller outperformed the conventional PI controller, not only in tracking the grid voltage phase and frequency, but also in terms of the PLL performance within the VSI controller, and the performance characteristics of both PLLs show very well that the FLC-based SRF-PLL outperformed the traditional one. As you can see here, the overshoot is less. It is 0.32, almost 33% compared to 7.9% in the case of the traditional one. So these results suggest that the FLC-based SRF could be a promising alternative to SRF-PLL. Conclusion: in this research, the modeling and design of conventional and intelligent fuzzy logic controllers for synchronous reference frame PLLs are presented. These PLLs were tested inside the 1 megawatt grid-connected voltage source inverter inside the current controller of this BSI. The different simulation results during normal grid conditions showed the effectiveness of both controllers in terms of detecting the phase angle of the grid voltage and tracking the reference. However, in terms of the performance here, the FLC-based SRF-PLL provided a better response compared to the PI-based SRF-PLL, and it reached a short settling time with a very low overshoot. These findings suggest that the FLC-based PLL could be a potential replacement for the traditional PLL, and much future work can be considered for this purpose. Thank you so much for your attention.